Okay, like before, I just wanted to make a quick video going through some of the problems from your homework, not the ones that are due, but ones similar to them, so you can get an idea of how to actually work through some of these. I'm not going to necessarily write everything out on here because some of these are pretty straightforward, and I'm going to assume you're looking at your book or have it handy, pulled up on your computer, so that you can kind of see as we go. But if we look, this is page 59, exercises 1.33 on continuity. Using the graph of the function, number one, using the graph of the function f in figure 34, determine whether or not f is continuous at x equals a. If f is not continuous at x equals a, what type of discontinuity is at a, jump or removable? And the quick sketch of the graph in more detail, look in your book, looks something like this. That's a right there. Is it continuous? Clearly not. That's pretty obvious. What type of discontinuity is it? A jump or removable? Removable discontinuity just means, can I kind of remove this dot and color in somewhere and make the function continuous? Clearly I can't here, because even if I do that, it still doesn't connect. So this is a jump discontinuity. It jumps from here to there. The next graph is the exact same. This one's going to be harder for me to sketch. It kind of goes up, down, has a little hole, goes up and does that, and then that's that right there. That's x equals a. Is that a jump discontinuity or a removable discontinuity? Clearly here, if I just removed that dot and colored it in right there, it would be continuous. So that's called a removable discontinuity. I can just erase it and draw it somewhere else and it becomes continuous. Here you can't, that's a jump. Okay, let's see. What else do we got? I'm trying to look for... Here we go. We'll do this one because this is another standard problem. And I honestly, because I don't have the homework I gave you in front of me, I don't actually know which of these I told you to do for homework, so I might end up doing some of those. Number 6 is the split domain function, or piecewise function, f of x equal to x squared plus 1 for x less than 2, 5 for x equals 2, and 3 halves x plus 2 for x greater than 2, continuous at 2. Is it continuous on R, the entire real line? There are different ways to do this. If this was 171, you could test if this was continuous without any calculus. It's a piecewise defined function. Graph that, graph that, graph that, look at the graph and see what you get. Here, I know this piece of the graph is a quadratic, that's continuous. That's a horizontal line, it's constant, that's continuous. That's a line, it's continuous. The only point that potentially causes a problem for discontinuity is x equal 2. So all I do is check that. All I need to do to check it is to plug 2 into each of those functions. If it's continuous, all 3 functions have to give me the same value at 2. That's the only way the graph connects. If they give me different values, then the function will be jumping around like the last graph we drew, which makes it discontinuous. So plug in x equal to 2. In the first one, 2 squared is 4 plus 1, 5. So the first one, yes. Second one, clearly it gives me 5. Third one, if I plug in 2, 2's cancel, I get 3 plus 2, which is 5. That works. All 3 of them will give me 5. Essentially, if you graphed it, at x equals 2, I get 5. So I'm not going to care about how accurate these graphs are, but at 0 you get 1, so it's going to like that. It's going to be a quadratic, then at 2 you'll get a hole. This one will be a line that at 2 gives me 5 at a positive slope, so it looks like that. And I have a hole in my graph, but here at x equals 2 I get 5, which colors in that hole and makes it continuous. Don't get confused here. That is not a line. This is a parabola, and then that's a line right there. But this is how you would draw it in 171. And you would see, oh, that hole gets colored in. It's continuous. Now we kind of have the calculus definition, but that's all we have to check. Is it continuous at the point? Since it's continuous at 2, and I know each of these graphs is continuous on their own parts of the domain, it'll be continuous for all r. That may have actually been a homework problem. Let's see. Let's see. Number 10. I'm not going to do number 10, but to just kind of give you an idea of how to solve it. Assuming you're watching these videos, it'll make it easier for you. Given the following piecewise defined function, given that right there, find C so that g of x will be continuous at x equals 3. Explain how you determine C. What would you do? Using the same logic that we had last time, for this to be continuous, at the differences in the domain, which are right here, both of these have to give me the same value. So what do I really have to do? Take x equals 3 and stick it into that function. Whatever this function would give me at 3 is what C has to be. Because that will then color in the open circle and make it continuous. I'm not going to find it for you because I know that's a homework problem and I want you to actually do it. But the principle is always the same. To get it continuous, make each value the exact same. Let's see. Oh, that's going backwards. This is forwards. And let's see. Okay, there was a couple that I wanted you to think about, so I don't want to do them. But let's see. Number 11, yes, because I gave you number 12. A child was born at a length of 20 inches and grew to a height of 37 inches by age 3. Can it be proved that this child was ever 30 inches tall? The child was born and he was 20 inches. So at birth, we'll say he's 20 inches. By year 3, he's 37 inches. Is that what it said? Yes. Can it be proved that the child was ever 30 inches tall? Yes. Clearly, I can define a continuous function. I don't have to for this, but I could. At year 0, I'm 20. At year 3, I'm 37. And clearly, on the interval 0 to 3, the function that gives my height or my length, whichever one you're using, as a function of time is continuous on that closed interval. So by the intermediate value theorem, there has to be some C in here that makes my height equal 30. In theory, there could be more than one of them according to the intermediate value theorem, but then you'd have to get taller and shorter, which probably doesn't happen. But clearly, there was a time when you were 30 inches tall. Let's see, number 12 was another version of that, but I want you to do that one on your own. I like that one. And then not really all that important, but I'm just checking the time on the thing. Good. Show number 14. Show that the following continuous function has a root between 1 and 2. And again, this one I am not going to solve out because I'm sure I gave it to you for homework. If not, that was an oversight. But we can at least see how to solve it. 4x cubed minus 6x squared plus 3x minus 2. A root between 1 and 2. What will we do? Well, if I'm looking for roots, I'm going to use the intermediate value theorem. This is clearly a continuous function on the entire real line. It's just a polynomial, which means it's continuous on the closed interval 1, 2. So if I want to find a root, don't use your calculator. That's not what we're going for. I'm not told to find the root. I'm told to show that the root exists. So find the value of the function at 1. if I plug in 1, this endpoint, f of 1 equals 4 minus 6, which is negative 2, plus 3, which is 1, minus 2, negative 1. Plug in this endpoint, f of 2. I get 2 cubed, which is 8 times 4, 32. 2 squared is 4 times 6 is 24. 32 minus 24 is 8. Plus 3 times 2 is 6, so that's 14. Minus 2 is 12. So at the left-hand endpoint, the function is negative. At the right-hand endpoint, it's positive. It's a continuous function. Clearly, there has to be some c somewhere in here where the function is 0. Keep in mind, and again, I do stress this from the intermediate value theorem perspective, the intermediate value theorem does not say that one root exists. It says at least one root exists, meaning there could be one root, there could actually be multiple roots in there. There's no way to know. You just know there has to be at least one, which is all I care about. I'm not finding it, I'm just showing that it exists. You can use other tricks later on to actually show or try to figure out what it is. But that should be enough of these. I'm not going to do another video doing examples of instantaneous velocity from the next section, because I already did a couple of them in the lecture video, and I don't want to make another video doing exactly what I did in the lecture video again. But those should be incredibly straightforward. And as always, if you have any other questions or if this isn't enough, feel free to call, email, or text me, and I will do more. That's not a problem.